in the last lecture briefly. So we were studying normal modes of vibration of a 3D crystal. Just give me 1 second. Right, so this is what we were discussing last time, and what we found is that if we have a crystal with then we have basically I'll modify this. So we'll have 3 acoustic branches, and so which at small k we have linear dispersion. And then if we have a 3D crystal with a basis that is, let's say, p atoms in the unit cell, then of course we'll have a total of 3 branches. I think last time there was a mix-up of notation, so what I wrote as capital N may confuse you with the number of unit cells you have in the crystal. So basically, the point I was trying to make is that if there are p atoms in the unit cell, then there is a total of 3 p branches, of which three will be acoustic branches, and the rest, that is 3p minus 3, these many will be optical branches. So these optical branches here would now have more branches, and the number will be 3p minus 3. So that's what we learned last time. So now what we'll do is, so see, the biggest problem we had with the classical treatment of lattice vibrations was that we got the contribution of these vibrations to the specific heat of the solid to be a constant, and which is not what experiments find. So that is the central problem that we will try to address. And now what we'll do is, instead of doing a classical treatment of these lattice vibrations, we will do a quantum treatment, and let's see if that improves the situation. So how will we do it? Most of the discussion will be, well, it should be clear as we go along, whether one is monatomic lattice or lattice with the basis. But let's see. So we are talking of 3D crystals. So I'll do this. So everything is in 3D now. I'm not writing it explicitly, but the important point is we're trying to do a quantum treatment of the lattice vibrations, and we have already discussed that there are in key points, in E equivalent key points, and if we are in 3D, then at each key point there are 3 branches to the acoustic mode. So we'll count 3 branches. So these are, if I have a monatomic lattice, then these are the 3n. So the oscillations at these nk points and the 3 branches, total of 3n. So these are the normal modes of the n atoms that we have in the crystal in 3D. So we can treat these normal modes, and remember we are working within a harmonic approximation, right? So we can treat these normal modes as sort of independent harmonic oscillators. So we look at lattice vibrations now as a collection of 3n independent harmonic oscillators. And we know how to treat harmonic oscillators in quantum mechanics. So that's one of the first exercises that you learn. So we'll apply that here, okay? So we have 3n independent harmonic oscillators, and we will we'll calculate their contribution to the specific heat, which is a straightforward exercise in statistical mechanics. So I'll just, to make things explicit, I'll just write down the notation that we are using here. So we have 3n normal modes, and this 3n number comes from in key points, and these sort of polarization directions I. So k has 8 values, and I is 1, 2, and 3 in a 3-dimensional crystal. Because these are independent oscillators, we can calculate contribution due to one of them and sum over all these modes. So the basic calculation is straightforward. As I said, it's a simple exercise in statistical mechanics. But after that, when we calculate specific heat in various limits, and particularly at intermediate temperatures, that's where further physical approximations sort of come in. So energy of each one of these oscillators. I'll use a sort of compound index. So S will stand for A and I taken together. So S is an index that runs from 1 to 3n. And I'm writing energy for one of those modes because it's a harmonic oscillator. Well, just to make matters explicit, omega S would mean this. So that's the energy. So how do we calculate specific heat due to this oscillator? Well, we'll have to calculate the internal energy, and in order to calculate the internal energy, we'll calculate the partition function. I'm not writing the index S here because yes. So this is the partition function for the mode S, and so this can be written as and then the contribution to internal energy due to this mode will be this. So 2 terms here, in the box. So this will simply give me and that term, if you evaluate, you will get into the so this you can identify as the zero-point energy of that mode, and thermal contributions come from this. Okay, so what is the specific heat? Of course, temperature derivative of this, and we'll normalize it by the volume. Right. So, so I'll have to erase this. So this is because of the mode S, contribution of mode S. Now, and if we have to calculate the total CV, then of course, I will take okay. Yes. And this term, as I said, is independent of temperature, so this will not contribute anything to the specific heat, only this term will. All right. From here, we can also write that this is the energy of vibration of the, of an oscillator of frequency omega s. So this factor 1 over e to the beta minus 1 is sort of the average occupancy, or it is the number of quantum vibrations in that mode with frequency omega s. Now, the first thing we do is to calculate, let's see what else I want to discuss. Yeah, so, so what we are doing is we are quantizing the vibrations of the atoms here. And so what we can say is, so this number n, so when we wrote ES is so here we can say that the oscillator in mode S is excited to a state ns. So ns at excited state. So this oscillator is in the ns at excited state. Equivalently, we can say that there are ns phonons of, let's say, frequency. So we introduced, I mean, I earlier used this word phonon a couple of times, but that was not quite appropriate. And we bring in the idea of phonons only when you quantize lattice vibrations. There are no phonons in classical treatment of lattice vibrations. So we can equivalently say that there are ns phonons of the type of frequency omega s. So it's perfectly equivalent to, parallel to when you introduce photons as quanta of electromagnetic fields. So here we are quantizing the lattice vibrations and calling those modes phonons. Okay, so this is the task here, to calculate the specific heat. And the first thing we do is to calculate the high temperature specific heat. So what do we mean by high temperature? So that we have to be very clear about. So by high temperature, we mean that we have, the solid is at a temperature where this quantity is small for all omega I k's that we have, even for the highest frequency phonon modes that we have in the system. This quantity is small. So that is our high temperature limit. So in that limit, so the temperature dependence, of course, comes from this term only. So now we call this x, and after that it's just a mathematical exercise. So I take this thing. Where x is a small quantity. So I sort of do an expansion of this thing for small. And in this, I pull out 1 over x. And because x is a small quantity, I take an expansion of this in powers of x. So then I have and then other terms. Yeah, so when you club these things, these two together, what you have is 1 over x minus half, and then you have a plus this should be plus. So you get a 1 over 12. Please check the signs, okay? I think I'm right, but I could have a problem with the sign. But anyway, so this times x, and then have our terms. So please check this sign. Anyway, now what was x? X was this. So when I have to calculate, so I'll put this thing here. I have this here. And then these things. So I have 1 over x, which is constant term. And so on. Now this, the first term, h cross omega s will cancel, and this, when I take d derivative, all I have is 1 over b sum over s. That's it. And this term, of course, does not contribute. There's no temperature dependence here. And this term would give me
Sir, it's a minus sign.
sorry?
Sir, it's a minus sign. The 1 over 12, it's minus.
Here.
Yes, sir. You have taken x common, so x square over 6 should be x over 6.
Yes, yes.
And there is no, I mean, the other term is not there, x by 2.
X by 2 is not there, you are right. Just 1 second.
X by 2 is there, the other term, x square over 6 is not there, actually.
1 over x, 1 minus.
It's 1 over x minus half minus x by 12.
Wait, 1 second. There was an x squared here. X plus half x squared plus 1/6 x cubed. Then I take a factor of x out here, so I have 1 plus half x plus 1/6 x squared. So this is correct. Then I expand this in powers of x. So I get 1 minus half x plus 1/4 x squared plus minus 1/6 x squared. So this is correct actually. So this whole thing was in the denominator, then I'm expanding this in powers of x. So you get this. So this 1 over x minus half. And when you combine these two, you'll get a factor. Sign is also correct. You'll get 1 over 12. And from x squared, you'll get a factor of x here. And here, when you take the t derivative, you pick up a minus sign. So there is a sum over s. T squared. Now let us make sense of these. So this basically means there's a factor of 1 here. How many modes do we have? We have 3n. So the sum over s goes over 3n terms. So I'll pick up a factor of 3n from here. So when I look at the first term, I get a contribution which is 3n over v kb. Now this n over v is simply the density of atoms. So that is 3n kb. Now this is exactly the classical contribution we had got when we did purely classical treatment of lattice vibrations and the corresponding specific heat. So the first term gives you the classical contribution, and the second term, by second term I mean this one. This gives you the quantum corrections. But remember, we are at high temperatures, so this would be large. So this contribution is small at large high temperatures. Number one. Number two, which we'll briefly discuss after we finish this part, is that when you are at high temperatures, the amplitude of motion of the atoms would be large, obviously, because they have higher thermal energy. And in that situation, the harmonic approximation is not a good one. You have to go beyond harmonic approximation. So basically, the anharmonic effects become more important, and so you don't really pick up this contribution. I mean, that's not the significant correction to the classical result anymore. The anharmonic effects are more important. So we'll see the consequences of an anharmonic effect maybe in the next lecture. So that's it. That's what you get at high temperatures. So now we'll look at the low temperature specific heat in a quantum treatment. So we take this term 1 over v. And sum over s would be sum over v n I. And we replace, I mean, as we have discussed many times, we can replace these k sums, 1 over v k sums by integrals. So we That's the first thing we do. Then, what is happening at low temperatures? So at low temperatures, which are the modes that will contribute? Now, obviously, the optical branches have non-zero frequency, hence energy at all k points. So when you are at very low temperatures, they are not going to contribute significantly. So we leave out the optical modes. However, because acoustic modes start from omega equal to 0 when k goes to 0, they will always contribute no matter how low the temperature is. So we cannot ignore the acoustic modes. So we include the acoustic modes. Number one, acoustic branches. So only acoustic branches. So with that, we make some simplifying assumptions. So what are these? So one I have already said, ignore optical modes. Number two is for acoustic phonons. This is the second significant approximation, that we take this linear form for all k, which is strictly valid as k goes to 0, but we take this to be the form at all k. Now, when is this valid? This is valid when my temperature scale is somewhere here, so that only these modes where the dispersion is really linear, they are excited, and the higher energy modes, even the acoustic branches, are not excited. So therefore, this approximation is valid when kBT is small enough so that acoustic modes within the linear regime are excited, and not the higher energy acoustic mode. And the third is, so this integral, of course, I should be explicit here, is over the Brillouin zone. As a third approximation, we replace this integral, replace this integral over Brillouin zone by integral over all of k space. All of k space. Now, how is that? So this factor in the denominator is e to this term h cross omega k over k minus 1, and kBT is small. So this h cross omega over kBT is a large quantity. So if we include k values, where omega is large, even then, because kBt is small, so the contribution of those modes would be exponentially small, so that sort of inaccuracies in replacing this integration over Brillouin zone by all over K space will be suppressed exponentially in the limit of low temperatures. So with these approximations, now the exercise is straightforward. You just have to evaluate that integral, take the time derivative, temperature derivative, and you get the specific heat. To make it explicit, we are only taking the acoustic branches. And then I'll probably not work out every step. I'll just indicate what is to be done. Otherwise, it's just straightforward. You define this quantity, I'm not writing the k cap dependence of Ci every time. Define that as x and transform the integral, and then of course you write d. And then you substitute these things into that integral. So in terms of x, so this integral will turn out to be this in terms of x. And so I'm writing this for a particular I. And the trick to evaluate this integral is that I take this x and so that basically becomes So then this integral is, apart from these factors. This is just to get, as you see, the numerical factors, because when you do this integral, you will get a number, okay? And the temperature dependence is here, which is t to the 4. So when you take a derivative of that, you will get a t cube. So that is already obvious. I'm just showing you the trick by which you can evaluate that constant. So this is sum over n. So there are terms similar in nature. So you can just evaluate it for a particular n, and then sum over n. And the way to evaluate that is to do integration by parts. So you can do that. And for a particular n, or rather what you get in the end is this constant times 6 over n to the 4. N equal to 1. Not 0. It is 120. And that gives you a constant which is pi to the 4 over 50. Well, in case you are interested in a quantitative result, but the temperature dependence is actually just in this factor over here, which is t to the 4. So as I said, if you take the derivative of that, you get a t cube term. So eventually, CV will turn out to be sorry, I have to define something before that. So here we are still working for a particular here there are 3 branches, 3 acoustic branches, right? So how do we do that sum? Well, what we can do is this is what is conventionally done, you can define an average C. So I'll write this later. And see, Ci depends on the direction of polarization, okay? So when I'm doing this angular integral in K, I can do an angular average and define an average C. So I define so this is sort of angular average of Ci's to be 1 over C cubed. So then obviously, when I do the sum, instead of writing sum over 1 over Ci cubes, I can write 3 over C cubed, where 1 over, sort of C is sort of the average of the 3 Ci's. So with that, you can substitute that in the expression there, in the energy expression, take the derivative with respect to temperature, and eventually you will get this. So this is this T cubed dependence of specific heat that we have been talking about ever since we started discussing the Drude theory, not the Drude theory, the Sommerfeld theory. Okay, so now we see how it comes about. It's the low temperature contribution to specific heat due to lattice vibrations. And you have to do a quantum treatment to get that correct expression. Okay, so we have done the high temperature limit, we have done the low temperature limit. In the high temperature limit, we got the classical result as the dominant contribution, so that is understandable. And in the low temperature limit, we got what is observed experimentally, the T-cubed behavior. But how high is really this high? What is this low temperature limit we are talking about in the context of real solids? Now, these are some things that we need to understand a bit. So, if you remember, now going back to the figure is a little complicated because I have to then stop sharing this screen.
Sir?
Yes.
Sir,
Yes.
are phonons spin zero particles? Because we are not putting any degeneracy factor in all
Yeah,
these
there are no
terms.
spins here, no.
Okay, sir.
So, yeah. So only at high temperatures that this approaches the classical result of luminosity. Now, what are these? I mean, let us try to have a sense of these numbers. So, let me try to show you this. So, I'll stop this for a while. So, these are measured phonon spectra of, I think, lead. Yes, so this is FCC lead. And these are measured phonon spectra. It's given in the textbook. So the highest modes are here, and at the zone boundary, you have, let's say, this longitudinal mode along the gamma X direction has this sort of frequency. So if we just take the order of magnitude, so these frequencies are of the order of 10 to the 12 hertz, 1.5 to 10 to the 12 hertz. So what is the temperature corresponding to that frequency? So if we mu is of order of 12 hertz, so if we want to have a sense of temperature corresponding to that, so can one tell me what sort of temperatures one is talking about here? Just put in the values of H and kb and tell me what this temperature is. Rough order of magnitude.
$100 Kelvin or so?
I'm sorry?
100 Kelvin, 10 to the power 2 Kelvin.
100 Kelvin? No. 100 Kelvin is a little too high.
Sir, it's around 10 Kelvin.
Yeah, maybe few tens of kelvins. Yeah, it doesn't go to 100 really. So if you put in the values of H and Kb, I think you will get something like 6.6 divided by 1.38, whatever that number is, multiplying 10 Kelvin. So if that number happens to be, say, something around 4, uh, yeah, maybe 30, 40 Kelvin. So a few tens of kelvins. That's the temperature corresponding to the sort of highest frequency modes that you see here. So at room temperatures, all modes are excited. But remember, the T cube law was derived when the assumption was that only the linear part is excited. Okay, the part in the acoustic branches where the dispersion is linear, only those were taken into account effectively. So that really happens at really low temperatures, and this sort of curve which we saw earlier tells you that the T cubed rise is only at very small temperatures. However, as you start decreasing the temperature from room temperature, very soon the specific heat starts deviating from the classical result. So therefore, there's a wide range of temperatures over which neither the low temperature limit nor the high temperature limit can actually explain the observed behavior of the specific heat. So this intermediate temperature regime is the problematic case. So now we'll attempt to treat that regime. So how do you calculate specific heat in the intermediate temperature regime? Okay, now let me stop this. So in this, in this, there are two sort of, if one may say, canonical approaches, given one by Debye and the other by Einstein. Some of you may have come across this earlier, may have heard the names. So we'll now try to understand these two. So one approach was given by Debye, which is called the Debye interpolation scheme, and the other was given by Einstein. So first, let us look at the Debye theory of specific heat. So first thing to realize in this is that you take, so first think of a monatomic lattice, okay? So we only have acoustic branches. So you take the 3 acoustic branches. And for the entire range of k values, you take a linear dispersion. Now, obviously, the dispersion is not linear over the entire Brillouin zone. So, how do you take care of that? So, what you do is, instead of integrating over Brillouin zones, I have deleted. So, we started out an integral over the Brillouin zone. then there are these things. So this integral over Brillouin zone is now replaced by an integral over a sphere of radius kd. Now, how do you choose kd? What is kd? kd is chosen in such a way that this sphere contains exactly the same number of k points that are contained in the Brillouin zone. So let's be clear about that. So there are n k points in the Brillouin zone. So this sphere of radius kd also contains n k points. From this information, how do we calculate kd? What is the volume in k space for each k point? In the reciprocal space, is well, V is the real space volume. So if we have n number of k points, then I must have this has to be equal to the volume of the sphere of radius kd. If you notice, it's very similar in spirit to how you define the quantity Rs in case of an electron gas. There, one is talking of real space volume, here one is talking of k space volume. And so this will give you a relation between the density of atoms, n over V, and kd. So what you have is and this is sort of a relation that is similar to the relation between electron density and the Fermi-Webb vector. Okay, except for the factor of 2. So this is what you have. Anyway, let's not worry about electrons right now. So this is what you have, and this will be useful later on. All right, so what have we done? We have replaced all the acoustic branches everywhere by a linear relation, and then we have replaced the Brillouin zone integration by an integration over a sphere, such that this sphere contains exactly the same number of k points that the Brillouin zone contains. And that gives me a relation between k. So that basically gives me kd. Okay, so okay, so when you put in these things in the expression for energy, the CV will be given by where, of course, dqk has been written as 4 pi k squared d So now the task is to evaluate this. Again, so what I'll do here is I'll indicate the steps and you have to sort of do it yourself. But before that, let me define certain quantities that are sort of standard in this literature. So one defines something called a Debye frequency, which is such that so basically the energy of the mode at the highest highest A that we have is equated to an angular frequency. So the omega. So that is u omega. One also defines a Debye temperature. I'll write it as T, which is H cross. So that obviously defines a temperature scale corresponding to the highest frequency phonons considered in the model. Now, before I go into calculation of CV, let me just make one important point. So here we are talking about only acoustic branches. So these three that you have here, this factor of 3, is because of 3 acoustic branches. What if you have a solid with a basis? Because the other modes are optical modes. Okay. Okay, so there what you do is you take a larger volume of the sphere so that the number of K points, so if you have, let's say, 3 optical branches, so the number of K points have to be doubled. So you take a radius of the sphere accordingly so that now it contains twice the number of N K points. So that's how this is treated within the Debye model. The important approximation is that everywhere the dispersion is taken to be linear, and the radius of the sphere is adjusted correspondingly. Okay, so with that, let us see how we can calculate CV and what we get out of it. So we'll use this. So the only temperature dependence that comes here is in this term. So therefore, what you have to do is take the temperature derivative, and what you get is, okay, there has to be a factor of 1 over V, because we are defining it per unit volume. Wait a second. That 1 over V was in the K sum, and when we replace it by integral, that is taken care of. So I don't need to worry about that. So all I have to do is to take the temperature derivative of this. And And after that is this, it is just a manipulation of the term. So again, let me indicate what you really have to do. So you introduce this quantity x, which is h cross c q over k dt. So, and from there you can write, you get a factor of k to the 4th. There's a k cubed here, k here. So you will write k to the 4 in terms of x. And we will write, of course, dk in terms of dx. And put this into the integral. And also, because this integral, the k integral goes from 0 to kt, the x integral would go from 0 to td over t. So with all of that, let's see as now, after this, there is a just a trick one has to use to get it in the standard form that we see is given in the book. So basically, that's where this relation becomes useful. So this part is straightforward from there, and then you have to use this relation. So from here, you can write 1 over 6 pi square in terms of sorry, no. So basically, you write 1 over 6 pi square in terms of n over kt cubed. Replace kt cubed in terms of dt cubed from those relations, and this is what you will get. So why are we doing this? Because then I can write this as 6 pi square and bring in a factor of 3 in the numerator also, so I get 9 there. This is the standard form that is in which it is written in all texts. So when you do all of that exercise, you will get and then this x integral. So this is the form you will see in the textbook. So here, the specific heat of a solid is expressed in terms of a single parameter, which is Td. Now, this is still a parameter. Okay. So how do you match with real materials? So one possibility is that you evaluate, I mean, you have measurements and then you match this expression with the measured specific heat, phonon specific heat, and from there you extract the value of Td. Okay, and if you match with the low temperature results, what you will have. So let us look at the low temperature limit of this expression. And I'll just give you the result because low temperature meaning T goes to 0. So therefore the Td over T in that integral, that Td over T can be taken as infinity. So you do an integral from 0 to infinity of this, and then I'll just give you the result of that. So this integral. So this will become the integral and the value is this. So there's a factor of 4 here. Okay, so then Cv becomes, you can just put that in and you get T over Td cubed. And if you have your measurements of Cv as a function of T, from there you can extract this parameter Td. So let us look at some of these values to get a sense of what we have. Yeah, so this table gives Debye temperatures for some alkali halide compounds. So few hundred Kelvin. Okay, these are given in Kelvin. So a few hundred Kelvin. Now alkali halides are, of course, they have strong ionic bond. Now when you go to elemental solids, let us look at some elemental solids here. These are typically, particularly for metals, these are much lower. And also, as you see, as you go down the group, so for example, when I take group 1 elements, lithium, sodium, potassium, as you go down the group, the Debye temperature decreases. And that's because, well, these are heavier atoms, so the bonding becomes weaker, so the phonon frequencies become smaller. And the atoms also become heavier. So these two combining, typically, as you go down a group, the Debye frequency and corresponding the Debye temperature decreases everywhere. So lithium, sodium, potassium, you look at beryllium, magnesium, calcium, and if you look, for example, zinc, cadmium, mercury over here, or copper, silver, gold, everywhere, as you see, if you go down the group, the Debye temperature decreases. Okay, but nevertheless, we are talking of a few hundred degrees Kelvin. right. So that is the Debye model. And so what does one do in the other one, the so-called Einstein model? In the Einstein model, what is different is the treatment of the optical modes, the optical phonons. And the approximation is very simple. You forget about dispersion of the optical modes. Okay, forget about the fact that their frequencies are functions of k. You just consider them to be all have some frequency omega e. So they all have a constant frequency omega e. So things become then fairly simple. If we take one of these modes, its contribution to the energy density of the solid would be so this n here is the sort of number density, capital N over V. And if you have if there are p branches of optical modes, then you just multiply that by p. So So given this, you can easily calculate their contribution to the specific heat. So CV, contribution to CV of the optical modes is just the temperature derivative of that. So it is E. Okay, so I can write it like this. And so this is straightforward. So what we'll do is we'll just look at two limits of these. One is the high temperature limit. And there, so what is that limit? So this is a small quantity there. Okay, if this is a small quantity, you expand it, take the leading order terms. So the leading order term in the numerator is square of this. And in the denominator, you will have, so there's a -1 here, so the 1 will cancel, and you will again have square term. So basically, they will cancel out, and you will get a constant, which is just this. So at high T, which is exactly the Petry's law. If you have 3 modes, P is equal to 3 optical modes, then P is equal to 3, then you'll get 3 NK. You recover the classical result. And if you are at low temperatures, then these numbers, because of these exponential factors, the contribution will be exponentially small. So they will not contribute. I mean, their contribution is exponentially small. That's the sort of more accurate statement. Okay, so that's the Einstein model. So what are the differences between these two? So in Debye model, you treat all branches to have linear dispersion. In the acoustic mode, of course, the problem is less in the sense that at low K, you really have linear dispersion. But if you have other branches like optical branches, then of course they are not linear, but you adjust for that by taking an appropriate sphere in the K space over which the K integration is done. So that that sphere contains exactly the same number of K points that you have in the Brillouin. So if you have only the optical modes, if it's a monatomic lattice, then you take the sphere radius such that there are exactly capital in number of K points in the sphere. If you have in addition optical modes, then the number of K points would have to be doubled. And you adjust the radius of the sphere accordingly so that it now contains twice the number of K points, and so on. In Einstein model, the acoustic modes are treated exactly as the Debye treatment, but the optical phonons are taken to have a constant frequency, which is independent of K, independent of which mode, which branch you are talking about. They have a constant frequency, and that's how you evaluate the specific heat. And what you get is, and we just looked at the two limits of that expression on the board. And in the high temperature limit, you get the classical result. And in the low temperature limit, their contributions are exponentially small. Not surprising because they have non-zero energies at every K. So therefore, at very low temperatures, they are not really excited. So they have no contributions. Any questions up to this? Okay, let us now have a comparison to get a sense of what are the electronic temperatures, what are the temperature scales, what are the phonon temperature scales, and so on. Let us so basically let us compare the electronic contribution to the specific heat that we calculated in the Sommerfeld model, and this lattice contribution to the specific heat, and get a sense of ratio of these two to understand which one dominates in which regime and so on. So what is the electron specific heat? So this Ne is the density of electrons. And the phonon specific heat, the low temperature. So the low temperature specific heat. We just wrote this expression a little while ago. So let us look at the ratio of these two. So what we calculate is, oops, and the sum on cancellation of constants and so on. Let me write this. So we are taking a simple situation where we have, let's say, monatomic lattice, and each atom has Z valence electrons. Okay, if Z is the number of valence electrons and the atomic density is N, then the electron density will be Z times N. Z could be 1, 2, 3, whatever. Right? And so that will give you now I can write epsilon F as kPtF. Okay. Right, so that's the ratio of these two. Now, so what we are, so let us find the temperature at which this ratio is 1. Okay, so if I call that temperature T0, then, so we are calling some temperature T0. So then you get T0. So you equate that to 1. So what you have is, you plug in these values, check this out. Okay, now can we make some sense out of these? What is TT? We saw TT is of the order of 10 to the 2 Kelvin. TF is of the order of 10 to the 4 Kelvin. So this is Z. So this is already 10 to the minus 2, then there is a square root. Z is something order 1, not very large. So T naught, okay, and as the temperature, first of all, T naught is a small fraction of T, number 1. Okay, I'll get something like 0.1 from here, there is a 0.1 here, so it's 10 to the minus 2. So T naught is something like 10 to the minus 2 of TD, the Debye temperature. That is point number 1. Now, as T becomes larger than this T naught, then this ratio becomes less than 1. Okay, so it is 1 exactly at T naught. As T becomes larger than T naught, this falls below 1. So therefore, the electronic contribution becomes small once T exceeds T naught, and as we see, T naught is a very small temperature of the order of few Kelvin. So therefore, beyond a few Kelvin, the phonon contribution dominates, and that was the problem we originally mentioned, that when you look at only the electronic contribution, let's say within the Sommerfeld model, you get a relation that specific heat should go like T, but experiments don't see that except at very low temperatures. Now, at very low temperatures, let's say below T naught, you have both electronic and phononic contributions. If you can extract out the phononic part, then you would get a linear T behavior. However, as T exceeds T naught, the electronic contribution becomes smaller and smaller, and it's dominated by the phonon contribution, which is not proportional to T anywhere. So therefore, so now we understand the situation with temperature dependence of specific heat much better. That once the temperature exceeds a few Kelvin, it's the phonon part that dominates, number 1. Number 2, to get the proper correct temperature dependence, you have to go to a quantum treatment of lattice vibrations. The classical result is not adequate as you start going below room temperature. The last point in this is that there may be quantities which depends on phonon density of states. For example, you are doing scattering experiments, neutron scattering, for example, to measure phonon dispersion, or there is some electron phonons processes going on in a solid. These things may depend on the number of phonon modes you have at a particular K. So just as in the case of electronic properties, we had to evaluate, so just as in the case of electronic properties, we had to evaluate quantities that depends on electronic energies. In case of phonons, also, we may have to evaluate things that look like this. Where capital Q is some quantity, some function which depends on the phonon frequencies, which are themselves functions of K. So this can be then replaced by an integral over K Now, these can be then defined as, or rewritten as, so instead of doing an integral over K, I can write this integral over omega when I take care of how many omega states there are in a particular region of K space. So this G of omega is the phonon density of states. It's exactly parallel to electronic density of states. You have a sort of band, you have dispersion, you have omega as a function of k. So when I have to evaluate these quantities, instead of doing a k integral, I can write this as this, with g omega giving me how many omega states I have in a given range. So that is the phonon density of states, and exactly as in case of electron properties, I can rewrite this as a surface integral of this. And just as you encounter singularities in the electronic density of states because of a particular structure, nature of the band structure, you get similar singularities in the phonon density of states, the same Van Hoff singularities, because phonon energies are also bounded functions in the Brillouin zone, so they have maxima, they have minima, so the derivative, k-space derivative vanishes at some points, and you have the same kind of Van Hoff singularities which can actually be observed. So I ask you to, I mean, there's a sort of plot of phonon density of states for aluminum, I think, given in Ashcroft's book. There are other examples given in Marder's book, so you can look those up. But the concepts are the same, so I don't think I need to elaborate anymore. So that's it about phonons, lattice vibrations within harmonic approximation. And next time we'll see why that is not adequate and one needs to go beyond harmony. There are phenomena that you just cannot explain, very common phenomena that you cannot explain within the harmonic approximation, and you have to go beyond that. So that is something we'll take up next time. So do you have any questions at this point? Aman, any questions?
No, sir.
Okay. Anybody else? Well, if not,